tutorial. Today we will be having it here because we don't need a laptop or a computer as Rajib told, and tomorrow onward we will have in PC Lab 5, that is on ground floor. So today's topic is Introduction to Metabolic Network, and Professor Rajib.
Good. So if you look at the schedule of the lectures, tomorrow we will be talking mostly about how you can build a metabolic network. Today's lecture is not on that. It sounds like I am putting the cart before the horse, but I have a reason why I am doing it. So bear with me. So this lecture is basically, let's say hypothetically, you have a metabolic network. How to use the network, analyze, and as we have discussed many times in the past 2 lectures, like how can you come up with predictions that will help you to design a microbe or to design an efficient experiment. So that's the focus of this lecture. All right. So many of you, since you have mentioned, at least not many, some of you are either working on a metabolic network or you want to know about metabolic network model. So let me ask you this question. If I say metabolic network model, what does that say? What is a metabolic network model? If you just typically think from a network perspective, what are the nodes, what are the edges, what do they represent? Tell me.
Metabolites in the nodes and reactions in the
Edges. Okay. Are we all on the same page here? So basically, if nodes are metabolites and edges are reactions, so basically it's an interconnected system. So the first principle of metabolic network modeling is the assumption which is called pseudo steady state. So it basically says that there is no change of concentration of a metabolite with time. Now when I say this thing to you, people who are basically working in the experimental biology area, you will probably are having a good laugh at least inside you, that how is it possible? It doesn't make any sense. How can you assume that a cell or a cellular system is under pseudo steady state? What is the argument here? Can anyone take a guess, like why we are assuming pseudo steady state?
There is a production, but it has reached an equilibrium position.
So you are saying that yeah, there is production, but at that stage there is no change of concentration. So it's kind of, you are thinking, where is my chemical engineering folk? He is not here yet, right? Okay. So in chemical engineering, continuous stir tank reactor CSTR operates in this kind of assumption. So there is no change of concentration. The concentration across all these different points in that reactor is the same. So that's one of the reasons actually. The major reason why we can assume this kind of a time frame or this kind of an assumption is basically we all know about the regulation and signal transduction. Now you have to do a comparative analysis. So the time it needs to regulate a gene or to have a signal, compared to that, this turnover rate of a metabolite is very small. That's why we assume pseudo steady state. Does it make a little bit more sense now? The other reason is we all know about the cell cycle, right? So if this is the cell cycle, or the stationary phase is not like that basically, then what's happening in this phase? This is the exponential growth phase, right? So what this approach basically does, it solves the model at a discrete time point. So if this is the continuous time frame, what I am asking you, discretize the time frame. Now what you could do, solve this model, and again I haven't really talked about the model, but the network model basically you can go and solve it for each of this time point. with the assumption. The assumption makes more sense in the exponential growth phase. Why? Because one of the other thing that we would like to do is to maximize growth, and growth is maximized in the exponential growth phase. So, that is why we assume pseudo steady state, and that is why sometimes we assume growth as our objective, which will not be the case at the stationary phase or the death phase, right? Does it make sense? Okay. Now, you might want to look at that screen. So, the way we set up the problem is just to write the mass balance or the mole balance equation. So, let us say you are dealing with a system like this. You have two reactions, A is making B, B is making C. What I am asking you, can you write the mole balance equation for the component A? To do that, what are the information you need? What are the pieces of information you need?
What is making it and what is converting into?
Yes. What else?
Rate of
Stoichiometry. So, for simplicity, let us assume the stoichiometry is 1. 1 mole of A is making 1 mole of B, 1 mole of B is making 1 mole of C. What else? I heard something else.
rate of decomposition of it.
Rate of decomposition, in other words, rate of reaction. So, from the reaction kinetics, you could assume that the rate of this is, let us say, K1 Ca, right? If I assume just a very simple kinetics, you can do that. You can do the same for the rest. But we will take a slightly different approach. Rather than looking at this rate as R, we will consider the flux through this reaction. We will call it as V, which represents flux. So, V is basically reaction flux. So, let us call this reaction as reaction 1, call this reaction as reaction 2, let us call this flux V1 and this one as V2, right. For the time being, let us assume that is what it is. We have a reason why we do not consider this, because for the intracellular reactions, it is very difficult to measure the kinetic parameters. All these K's, yes, you can do it. For E. coli at least, we know that at central carbon metabolisms, K values are known for E. coli, and if you are measuring something which is being excreted out of the cell, that is easy to measure. If it is something that is getting inside of the cell, that is also easy to measure. But what is happening inside the cell, if you would like to do that for a non-model organism, it is not that easy. So, we are taking a slightly different approach. We are focusing on the flux V. Now, let us write this balance equation. Let us say the way it operates, it is basically on the left hand side, you need to consider the rate of accumulation. So, basically the rate of accumulation is equal to what? Inflow minus outflow plus generation. We know that. This is plain and simple mass balance. So, think about that concept and think about how we can write the mass or the mole balance equation, not for that system, but let us try to write it for this system. So, what will be my dA over dt, dV over dt and dC over dt? What is dA over dt? What is the change? How can we write the equation for the change of A? Negative minus V1. What about B? Plus V1 and what about this? Just V2. Now, you see what's happening here. If you would have used the rate equation here, you have to introduce all these K's and concentration. So, we are simplifying it by saying these are just flux values. What will happen now, as I said, we are operating under pseudo steady state. So, if it is under pseudo steady state, then this is 0, this is 0, this is 0. So, from the time domain, from an ordinary set of ordinary differential equations, you are basically converted everything to a bunch of algebraic equations. And from this framework, you could easily guess that these are all linear equations, right? We have learned how to solve linear equations. We can use Gaussian elimination, Gauss-Jordan method, so many other things. But what is the one condition that you need to have to solve a linear set of equations? Tell me that one condition that you need to have to solve a linear set of equations. So, let us say you have 3 different variables. How many equations you need? 3, at least 3. So, if you have more or less, what will happen? Let us say you have 2 equations, you have 3 variables, or you have 4 equations for 3 variables. What will happen? How we actually solve this kind of problem?
All the other variables are expressed in the form of in terms of one variable, and depending on the change of that variable, other parameters.
Okay, that is one scenario. What about the reverse scenario? So, two things. So, what I am basically asking, number of variables and number of equations. So, I asked 2 questions. What will happen if the number of variables are more than the number of equations or less? You answered one question. What about the other scenario?
If it is more, then we'll have answers which will
Under and overdetermined. Yes, that is the technical term. So, how do you deal with this? Yeah, go ahead.
then there comes the idea of consistency and inconsistency.
Okay.
Some of the solutions will be inconsistent
Mhm.
with few of the equations,
Okay.
but otherwise some will be consistent.
Okay. All right. Do you want to add anything? How do you deal with an underdetermined or an overdetermined system? In general, forget about this flux. Let us think about mathematics.
If a system is underdetermined, that means there are less number of variables.
Yes.
So we put more variables, like we try.
So, in other words, we would like to make sure that the number of variables actually are equal to the number of equations, and we can solve it. If it is an overdetermined system,
Then it's good for us. We can verify the system for the extra variables.
okay. So, what we all agree is to solve a system like this, we need to make sure that the number of variables should be equal to the number of equations, then it is a plain and simple method. In real life, do you think that is the case? In real life meaning metabolic network model. What is happening here? How many variables you have? 2, right? How many equations? So, we have a problem, right? So, what I am basically trying to get here is that the concept of optimization. If it is just the total number of variables being equal to the number of equations, all of us could just solve plain and simple, like by using Gaussian method, Gauss-Jordan method, and we can solve for V1 and V2, and it's fine. But in real life, in metabolic network model, this is what you will deal with. So, your number of variables, which are fluxes, will always be less than the number of equations. So, it is an underdetermined system. If it is an underdetermined system, you cannot just plain and simple solve it. You have to apply a different method. Does it make sense? Now, if you look at this simple network on the screen, you could see that basically we have x1, x2, x3, x4, x5 and x6. So, we have 6 different metabolites. The V's are the fluxes, and if I ask you to write the balance equation as we have done for these simple cases, can you do it? So, let us do it as a class. Draw this metabolic network on the piece of paper that you have and try to write the balance equation. So, I will let you first draw the metabolic map and then let us do it. It is very simple, but if you do not get it right, then I cannot move on and discuss. By the way, so this is the system boundary. So, in our case, basically let us consider this as a cell membrane, and V in is basically the nutrient which is being uptaken by the system. It could be carbon dioxide for our case, since it is a photosynthetic microbe, and V out 4, 6 could be product or byproduct, take your pick. So, within this system, let us try to write this balance equation for component 1 through component 6. So, I will be walking around. If you have any question, ask me, but I do not think I can walk, I will be out of the frame, but anyway. If you are done writing the balance equations, then I will need you to write the number of unknowns and the number of equations. Yeah. Okay. Sure. So, for this one, right?
dx by dt.
Yeah, just let us write for dx1 by dt, right? So, that is the change of the concentration of x1. So, on the right hand side, you need to think about what is coming in minus what is coming out. So, what is coming in is V in 1, right? What is coming out is V1. So, it is V in 1 minus V1, and same thing for all the metabolites. Does anyone have any question here? Are you, so can you come here if you are, so basically what I am saying here, same thing. So, if you write dx1 over dt, you have to consider what is coming in and what is going out. So, what is coming in is V in, what is going out is V1, right? Make sense? Any question for me? So, as I said in the example, if you are struggling, could you come here so I can talk? So it's plain and simple. So this is the change of the concentration of x1, right? So for that matter, you have to think about input minus output. What is the input? This one, right? So that would be like plus VIT. What is the outlet? V1. Now for x2, V1 is the input, V2 and V3 is the output. So it would be V1 minus V2 minus V3. Make sense? Do you need any help? Okay. If you all could come together. So basically it's the same concept as we have discussed. So we are interested to find out the change of x1, right? So dx1 over dt. And as I said, it's in minus out plus generation. So there is no generation term here. So this is 0. Think about input. Input is Vn1, right? What is the output?
So V1.
V1, excellent. Now if you think about this one.
Here V1 is the input.
Exactly. The output is
V2 and V3.
V2 and V3. Excellent. So now you can follow along, right? Do you need any help? So one thing is, when you are thinking about dx1 over dt, you have to think, you are fine. Output is V1. But what about the input? You have an input which is V in 1. Oh, sorry. So this is
Not
V in.
in minus
Yeah.
V1.
Right.
Input minus
So last one is out. Okay. I will. Yeah. So the last one is, I think, out 4 and out 5. But anyway, it doesn't matter. Do you need my help?
Somewhere like this.
Yeah, you're fine. Are you good?
Here you have to put 0 or out.
Just put out, because it's an output flux, right? Are you fine? You're fine. Good. Are you struggling?
Yes, sir.
Okay. So, as I said in that example, you need to write it for each of these 6 metabolites, right?
These are 6 metabolites.
These are 6 metabolites.
And
These are fluxes. What, like flux? Think about a flow of something that goes through the metabolite. So this is int, this is out 4, that's out 5. Now if you are focusing on this, dx1 over dt, tell me what's the input here.
dx1 over dt.
Yeah.
It is the change V int minus V1.
Exactly. For this one, what's the input?
Change in x2
Yeah.
time is V1 comes in as flux
Yeah.
minus V2 minus V3.
Exactly. Are you fine?
Yeah.
Okay. All right. Any confusion?
I don't understand.
Okay. So